All right. And now that my surface is working, because they replaced it, so life is good. So I'm going to transfer my volume to my surface. Can you guys hear me okay?
Yeah.
Oh, super. Yeah. Ah, so nice to be mobile again. Okay. So today we get into rectangles with a fixed area. So up until this point, we've dealt with primarily straight lines, right? Correct?
Yeah.
Okay. So it says, here's our focus for today. When the product of two variables is some fixed number, what is the pattern of change, and how is that pattern of change reflected in tables and graphs and the relationship? Okay. So we have a pattern. You're going to look at patterns in length and width of fixed for rectangles with a fixed area. All right. So we have a table here. Okay. It's written 1 through 8, and this rectangle has an area of 24 square inches. Who can remember how do you find the area of a rectangle or a square? Because it's the same equation formula.
You do length times width.
Very good, right? Area equals length times the width, right? So if the area is 24 inches, and if you look at the table, our length is 1 inch, what would be our width? Hello? Come on, we have a 2-day week here. Let's go. Let's participate. If if length times width equals the area, our area is 24 inches, and I give you a length of 1 inch. What would be the width?
24.
24, right. It would be 24. Because 1 times 24 is 24. What if the length was 2? What would the width be? 12. Because 2 times 12 is 24. What about for 3? 8.
6.
8. It is 8, right. 8 times 3 is 24. 6 was close. What about number 4? If the length is 4, width is?
6.
6. All right. So, and we know going the other way then over here, this should be 4 and this should be 3, right? Because these are just flip-flop. So 5 and 7 don't go evenly into 24. So if you take 24 and divide it by 5, you get 4.8. And then 7, I think we had to round it. It's 3. Okay. Now, when we've had values of linear models, what in the tables, what always had to happen in the tables for it to be linear?
Constant rate of change.
Very good, a constant rate of change. If I look through the y's here, because the x's go up by 1, right? But if I look through the y's, is this a constant rate of change?
No.
No. So let's graph this and see what happens. So if our length is on the bottom, 1, 2, and notice how the graph is labeled. Okay. Every time when we do a graph, your x and y axes should be labeled. And if I go up by 3s, we should be able to get all the data in there. All right, so at 1, we were at 24. At 2, we were at 12. At 3, we were at 8. Close enough. Oop, did we lose somebody? I'm getting Rudy back in here. At 4 is 6. At 5 is 4.8. This is going to be a tough one, so I'm going to do 4. So 4.8's got to be somewhere in the middle, just trying to do my best. It's hard to graph 4.8. 8 is 3, which means this one is like 3.4. So if you notice here, what do you notice about this line?
It's quadratic.
Not close. It's not quadratic because a quadratic actually looks like this. It looks like a U. Okay. But it's not linear, right? We know that for sure, correct? It for sure is not linear, okay? So it says here, describe the pattern of change in the width of the rectangle as the length increases. So I'm going to write the first part of the sentence. I'm going to see if you can finish it for me. All right. As the width increases by 1, what happens to the length? What does the length do? Look at your table.
Decreases.
Okay, the length decreases. Does it decrease by a constant rate of change?
No.
No. It decreases by a non-constant rate of change, the crop, okay? That way, when you write that, if you just leave it at decreases, they say, well, okay, it decreases. If you tell them it decreases at a non-constant rate of change, that's more specific because you're telling them that the numbers are the same every time. So you automatically know just by reading that statement. If you were to read that statement without a table or a graph, you would know right now that that line is not linear because you wrote non-constant rate of change. And if you wrote constant rate of change, they would know that it's a straight line just by reading that sentence. Now look at sentence number 2. Is the relationship between the length and the width linear? The table above in the graph, is that linear?
No.
No. Nope, it's not. And again, because it has a non-constant rate of change. If it was linear, it would have to be a constant rate of change. So if we were to write an equation, and when Sky racking back up, there you go. If we were to write an equation relating the width to the length for the rectangles with an area of 24 inches, we could just write length times width equals 24, right? Now let me show you something a little neat here. If we had to solve, we were trying to solve for the length, right? So I'm going to box this in just so, but watch what happens. When we were trying to solve for the length, right? So to do that, if we divide both sides by W, wasn't this what we were doing to find the length?
Yeah.
Yeah. So again, you can get the same answers as this equation, right? Because isn't division the opposite of multiplication? And if we wanted to solve for the width instead of length, it would be the same thing. It would just be this. And again, you could still get the same answers as you would over here. Okay? Because that's what we did. Some of you were taking 24 and dividing it by the width to get your answer. Some of you were thinking, okay, what times 1 gives me 24? What times 2 gives me 24? So we were kind of doing all the same things as these three equations. These three equations, even though they're different, they look different, will give us the same answer. Okay? Are we good? Can we move on?
Yeah.
Yep, okay. Just making sure we got it. So now we're going to change the area. Okay? Now we got a rectangle with an area of 32 square inches. And remember, area always deals with square units, right? If I give you a rectangle and I give you the length of a side, right? That's usually just in inches, right? Because we're just talking about a length, right? We're talking about a length from here to here. Remember, area is everything inside of this. That's why it's got to be square inches, okay? Which sometimes we write it as this. So think about what we just wrote as an equation. What can we write an equation for this model? Remember what we just wrote on the previous page.
L times W equals 32.
Good. Length times width equals 32. And if we were to solve for one and the other, you could also have it like this. Right? These answers here would give you the same answer as this. Right? All right, so we have a table here. Now remember, 32. All right, so this is dealing with a rectangle with an area of 32 square inches. So again, if the length is 1, what is the width?
32.
32. What if it's 2?
16.
Good. 3 is a decimal. I'll give you the answer. It's 10.6 repeating. I have a calculator. What about 4? 4 times what gives me 32? Or 32 divided by 4 is what?
8.
8. 5 is 6.4. We're going to try to keep everything just to a tenths number. These numbers aren't. And then these are flipped, right? This is this. Okay, so we have our 10 values, length and width. So, writing the length on the bottom because that's where it's labeled. And then if I go by 3s again, I should have enough to get it there. 32 is just off the screen, so we should be all right with that. Okay, so at 132, that's like right close to there, right? Close enough. At 2 is 16. At 3 is 10.6. This is going to be a fun one to graph. Well, 10.5 is halfway between 9 and 12, so somewhere there. Hard to graph 10.6. And then 8 and then 6.4 and then 5.3. So you start to see the dots, right? Starting to look very, very close to what we just had, right? 8 is 4. 3.5. 3.2. So again, if I connect the dots, okay, we have our line. So let me tell you something about these lines. Someone said earlier, was this a quadratic? Nope, this is called an inverse. Whoa. An inverse variation. which if you look at your book, on the front cover, anyone got their book handy? Just out of curiosity?
I do.
All right. So can you guys see me on the, oh, you guys can't see me. There is a little title at the bottom, right? It says linear and what?
Inverse variation.
Inverse variations. This is the other part of the title of the book. All right. This curve will never touch an axis. And here's why. Okay. If I multiply anything by 0, what do we get?
0.
0, right? And here, we're supposed to get length times width equals some fixed number. Well, anything times 0 is not going to be that 32. It's going to be 0. So it'll go close to these, like this line will get closer and closer and closer and closer, but will never touch the x-axis. This line up here will go higher and higher and higher and higher, but never touch the y-axis. It's kind of trapped because, again, no number times 0 will give us 32 or 24. It's going to give us 0. So those can never be a solution or a point on our lines because, again, it just can't work out mathematically. All right. So down here, it says, what are similarities and differences in the equation? Well, remember, we had length times width equals 24 for the first one, and length times width equals 32 for the second one. So the similarities were they were multiplying two numbers to give us a fixed number, right? That was similar. The equations are similar too, right? That's like having y equals mx plus b, but we can have different numbers in that equation, right? To make different lines. Now, obviously, what is different? What's different is the fixed number, right? And sometimes we'll call this fixed number as a letter, refer to it as k. All right. So in a general formula for inverse variation, it's x times y equals k. And k is that fixed number. We don't use the letter C because we use the letter C for the word constant, and it's not. So k is that fixed number, okay? And that's the general form. And it can be written three different ways. It can be written this way. It can be written this way. And it can be written this way. All will give you the same answer. So another reason how it's different from linear is the linear equations had one equation, right? Only one way to write it. Correct?
Yeah.
Okay. This, you can have three ways you could write an equation for it and get it right. Now, what are similarities and differences in the graphs? Well, obviously the one big similarity is what? Between the two graphs on the first page and the second page.
They're both inverse variations.
Right, but what does the graph look like?
It's decreasing.
What does the line look like?
Inverse variation.
The shape of the line. I'm trying to pull the word out of you. It's both a curve, right? Don't they both curve, right? They kind of come down like this. Ooh, how come that line didn't show up on the board? Like that, right? So they both curve. The differences, probably if anything, is going to be the, I guess you can call it the steepness of the curve. The bigger this number, okay, it's going to have more of a bow to it. Where the smaller the number, the curve, okay, so it's going to eventually do one of those. Where the smaller the number, it's going to kind of curve really almost, you know, as close to a straight line as you can get a curve to look like, okay? Similarities in the table, okay? So remember, one variable is always increasing. The other variable will always be decreasing. Okay? That's the only way you're going to get it to go down. Okay? You're never going to get them where they're both increasing. And then they didn't bother to ask you differences in the tables because that's pretty obvious, right? We had different numbers. That's about the main difference. Okay? So this was inverse variation, your introduction to it. So I'm gonna go back to here, and then I want to, while we're still recording, so in our folder today, okay, because we are done, we have 24 minutes of class time. I recommend that you go into Tuesday's folder while this is fresh in your head and work on this right here. I don't know if this is going to write on the board or not. No. Okay. So under the assignment, there's 3 problems dealing with what we just did. And while it's fresh in your head, I'd say it's your best bet to do them. When you open this assignment, you can submit. Okay? You're going to have the submit button in here. All right. So this assignment will be graded. Please submit a picture of it. Okay? Now, again, I'm looking at you did the problem, just did it. Okay? I'm not expecting the first time you see this to do the problem correctly. Okay? You want to try to do it correctly, but if you make a mistake, that's how we learn from it. Okay? So you're gonna get a completion submission to get yourself some points. Okay? It is due by, that's not the right date, by the way. I'll fix that date. It is Monday, November 30th. At 8 a.m. That's when it's due. It says it up here. Oh, don't pay attention to down where it said below the bold. Up here, due date, Monday, November 30th at 8 a.m. Okay? I'm telling you, the assignment isn't very long. And when I turn you loose to let you go work on it, it's something that you could easily do before the end of the hour is over with. And then all your focus is from now until we come back from our break is the test. Okay, getting ready for it. All right. So let me I'm gonna take this back to here. I'm gonna stop our recording, so give me 1 second.